Hi guys, today I'm going over video solutions for the September Lunchtime 2020, and this contest is kind of special because I'm the editorialist for this one, which means I both know the solutions in advance and can get this video out early, basically right as the contest ends, because I'm prepared for it. So that means this should be kind of cool because it'll be just instant basically, instead of having to wait for upload stuff and processing and YouTube and all that stuff. Everything's done beforehand. So in terms of that, that's a nice benefit of this. And this video editorial is kind of designed to supplement the editorials I've written. So they're going to be the same approach, just kind of described visually instead of with text. So they kind of go together. You could possibly check both of them at the same time and then use one to understand the other or vice versa. Okay, so without further ado, let's get into all the problems. So first we have a watermelon, and the statement goes as follows. You're given some array of positive and negative elements, and zeros maybe. So for example, you have 2, -5, 0, and 7. And you can do a bunch of moves to this array. In one move, you can pick an index I. We'll label these one indexes here. You can pick an index I and then subtract I from that element. So here you'd be able to subtract 4, and then this element will become 3. And you can even do it again. You can do it as many times as you want on any element. Here you'd subtract 1, and then this would become 1. And etc. So using these operations, you want to modify the array such that the total sum of all elements is equal to 0. So the total sum of all elements must be equal to 0. Now this is doable. Basically, the way we solve this is with kind of just casework. Let's say, first note that, look at all these operations. We're always subtracting some positive number I. So all these operations are going to affect the array by changing it by some negative number. So we can only decrease the array with the operations. So if the sum is already less than 0, then there's no answer, because we can only decrease the array, and if we're already below 0, there's no way we can increase it to 0. So I'm going to make this S. And then otherwise, S, which is just the notation for the sum of all the elements, is greater than or equal to 0. And in that case, because we have this first operation, the subtract by 1, we can just subtract by 1 S times until we get to 0. And because everything's an integer, this is always going to work. So either the sum is less than 0, in which case there's clearly no answer. Otherwise, we can just subtract by 1 until we get 0, so we do have an answer. And that's kind of it. Okay. So now for GCD operations. We're given 2 arrays. One array is the identity array, basically. So you have indices 1, 2, 3, 4, and 5. Then each element in array A is equal to its index. So it's going to be exactly 1, 2, 3, 4, 5, 6, 7, and so on. You're also given an array B, where all BI is less than or equal to AI. So for example, this would not be a valid array because 3 is bigger than 2, and 5 is bigger than 4, but we can do something like 1, 2, 2, 1, 3, and that would be valid. So what we want to do is we want to transform A into B using some sequence of operations. And in one operation, we can do the following. We can take two indices, their original values in A, and then we compute their greatest common divisor, which is the biggest number such that both of them are divisible by it. So for example, this greatest common divisor of 2 and 4, which I'll say GCD, is 2, because both numbers are divisible by 2, and clearly you can't get bigger than 2 because one of the numbers is 2 itself. So yeah, you take the greatest common divisor, and then you replace both elements in A by it. And you can do this as many times as you want, but ultimately you have to have converted A to B. And you want to see if it's possible to do this. So there are a few things we can notice right away about kind of what's happening in this problem. So first of all, well, how do you begin this? So if let's say x is a divisor of AI, then either x is equal to AI, in which case it's just itself, or it has to be less than AI, because otherwise it just can't be a divisor. So x is less than AI. And what that means is that all divisors of AI come before it in the array. So for example, 4 has the divisors 1, 2, and 4. 4 shows up where it is, but all the other divisors come before it because these numbers are just 1 to n written out in order. And another thing we can say is that if GCD of AB is equal to A, then after the final operation, or if we do an operation with A and B, A is unchanged because A is the GCD. So these two things are useful. And the reason they're useful is because there's one final condition we can use to see if our answer is possible or not. And that condition is essentially absolute. So what can we really convert AI to? Because we can only set it to some GCD of itself and some other number, we can only convert it to divisors of AI. Because if something's not a divisor, it will never be a GCD of AI. So if any AI, or if any BI is not divisible by AI, or no, I guess if any AI is not divisible by any BI, then clearly we can't have an answer because, well, there's no way we can make AI into BI. We can only set AI to its divisors. So for example, in this case, 5 is not divisible by 3, and indeed there's no way we can ever get 5 to be 3. And 3 is not divisible by 2, and there's no way we can get 3 to be 2. So this case is impossible. But if I set it to something like, say like this, I'll set these to 1, 1, 3, 2, 5. Now, basically we can show that clearly if any AI is not divisible by BI, then there's no answer. But we can also show that if all A are divisible by BI, then there is an answer. And this is because it's like a result of combining these two things, these two ideas that we figured out. First of all divisors of AI are going to be before, like, in a previous element in the array from AI. And if we say AI is B, then we need to find some A to the left of it where the GCD of A and B is equal to A. Well, in this case, this is only true if A is B is divisible by A. Because if that's the case, then A is the GCD of itself, and also A is a divisor of B. And you can't get any bigger than A because A has to be divisible by it. So A is the biggest number. But basically, the only time we need GCD AB to be equal to A is if B is divisible by A. And if GCD AB equals A, then the value at A is unchanged. Which means that if we do an operation, say, on this element, and all of its previous elements are unaffected, then when we set this to 2, for example, we can do an operation with this 4 and this 2. Everything to the left is going to be unchanged. So it's kind of like this element is independent of all other elements because, number one, its operations are only going to affect itself, and number two, because its operations only affect itself, so do the other operations, and therefore no other operations we've done in the past have affected this one. So, because everything's independent, we can assume that none of these numbers have been changed. And because we have all the numbers 1 to AI previously, and all divisors of x are less than AI, it's guaranteed that BI is going to be somewhere in this range of previous values. And then just with a single operation, we can make it so we combine these two elements, and their GCD is going to be exactly BI. But again, this one is going to be unchanged, so it's only this one that's going to change to BI. And if we kind of do this for all elements going backwards, again, because they're independent, it doesn't matter the order we do it in. But actually, no, it does, kind of. But because they're independent, if we do it backwards, then nothing is going to affect anything else. Because if we're here, the only elements that we've changed so far are going to be to the right of it. But we don't care about elements to the right of it because there's no way they can be divisors of this element. We only care about things to the left, and we haven't changed anything to the left. So it works out perfectly. So the final condition ends up being if any AI is not divisible by their corresponding BI, then there's no answer. Otherwise, there is an answer. And that's kind of it. There's a lot of kind of a mathematical backing to this, but it ends up being very simple in terms of the final solution. Okay, now I'll go with the problem root the tree, where basically we're given a tree, except it's like directed. So instead of just having nodes and edges in the classical sense, every edge is directed from one vertex to another. Say, for example, like this, like this, like this, and like this. Or we can say even like this and like this. Just arbitrarily. And what we want to do with this tree is we want to give it a root. And basically a root of a directed tree is essentially it's a vertex where all edges point away from it. So it's kind of like In the traditional sense of a tree, it's kind of like the tree you think about when you have parents, essentially. You have an edge from a parent to a child in all the trees, except it's kind of just directed. And so in this tree, you can't have any edges that go like this, because then that would violate the root condition. Another way to define the root is that you can start at the root and then get to any other vertex traversing some series of edges. And in this tree, for example, this is always true. You can get here, and then you can get here. You can get here, and from here you can get to both of these. So you can get everywhere just from the root. And notice that no other vertex has this property. For example, if you're here, then you can't get up. You can't traverse this edge, so you can't get everywhere. Only the root has that property. So that's a rooted tree. And what you can do is, in one operation, you can delete an edge. Say just this edge is gone. And then now we're left with two separate components, the left side and one side and the other side of the edge we just deleted. So now, still as part of the operation, we have to add back in another edge so that it remains a directed tree. So for example, it would have to be from a vertex in this component to a vertex in this component. And the direction and the vertices we can pick however we want. So for example, I can add this edge in. And we want to find the minimum number of operations it takes to make the tree rooted. Okay. So remember how I said we can kind of think of this tree as like the traditional sense, where every node has exactly one parent except for the root. The root has no parents. Sad. Because, like for example, this one, its ancestor is this above node that goes into it, and similarly for this, and these two both have parents of the root. And basically, in any traditional, like, undirected tree, every node has one parent. And in the directed variant, we can think of it the same way. And because of the definition in the root where we have to be able to reach everything, we can say that the parent has a directed edge from the parent to each child. Okay, first we can show clearly that no vertex can have more than one parent. Because say they did, and we'll think of it like this, where parents just kind of go down. So we have two parents here, right? But just think about this. If we started here, we can go down here, but then we can't ever go back up here. And because this is a tree, we know there's only one unique undirected path between every pair of vertices. So if we can't get to this through this pair, or through this vertex, there's only one path, so that's the only path. And therefore we can't get through it no matter what. So if there's more than one parent, we can't get from one parent to the other. This edge is just a wall. And same for here. And if we start here, we can't get to either parent. So that clearly won't work. So every vertex must have at most one parent. So that shows that this is necessary. Now we'll show that this is kind of a trick for proving things. We'll show that it's like both necessary for this to be true, for there to be a solution, and it's sufficient, which means if this is true, there's always a solution. So if I claim that if all vertices have at most one parent, there's always a solution. Here's why. Consider some vertex. Okay, either it's the root, in which case we're done. Actually, we're basically going to prove that every vertex in this tree is reachable from the root. And to do that, we're going to go backwards up the parent edges until we eventually get to the root. And we'll always eventually get to the root. Well, we're at this node. So either this is the root, in which case we're done, or it's not the root. And if it's not the root, then it has a parent, because only the root doesn't have any parents. Every other vertex has a parent. So let's go up this parent. Now we're going to be at a different vertex. Either this vertex is the root, or it's not, in which case we can do the same thing. Let's go up this vertex as parent. And so on until we get to the root. Why is it guaranteed that we can get to the root? Well, because first of all, after every operation, this maintains its tree shape. So there are no cycles. Which means that in this process of visiting parents, we're never going to visit the same vertex more than once. Which means eventually we have to come to a stop because there are only n vertices for us to visit. And we can't stop on any vertex that isn't the root because that vertex has a parent and we can therefore go up that vertex into more vertices. So eventually, through some kind of like weird, it's not exactly like pigeonhole principle, but it's just some intuitive argument that basically says that if we can't ever visit a vertex twice, and the only place we can stop is the root, eventually we're going to get to the root. And once we do get to the root, then we know that we've traversed these edges backwards, but we can get from the root to this vertex using this using this path that we just created. So if we can get to the root, then the root can reach that vertex, and we can always get to the root, so the root can always reach that vertex. And therefore, the tree is rooted, because the root can reach all vertices. So if all vertices have at most one parent, first of all, it's necessary because otherwise it would be impossible, and it's sufficient because if this is true, the tree is automatically rooted. So now, all we need to do is basically turn this into an answer somehow. So all v having at most one parent means that, well, again, every parent has an edge from the parent to the child. So let's denote ID of I be the in degree of I, which is to say it's the number of edges that go from some vertex into I. For example, this in degree is 0, this in degree is 1, this is 1, this is 1, this is 1, this is 1. Notice a pattern there? Well, here the in degrees are, this is 1, this is 0, this is 1, this is 2, this is 0, and that's 1. So if any vertex has in degree greater than 1, so if IDI is greater than 1, because every parent has an edge from the child to the parent, then every unit of in degree I means an extra parent. So if in degree I is greater than 1, then we have greater than 1 parents, which of course is not allowed. So we also have to mandate that in degree I is less than or equal to 1, because the in degree is equal to the number of parents. Okay, now this is useful because now what? Let's focus on some vertex that has a bunch of edges going into it. For example, this has 3. Using some series of operations, we have to remove these edges. And we can imagine there's more graph, but this is kind of just a general place. So in one move, we can kill exactly one edge. So we can reduce the in degree of one vertex. This is decrement, essentially. So we reduce it by 1. And so minus, yeah. So let's say we get rid of this edge. Okay, now we have exactly n minus 2 edges. Which means and we also have n nodes, which means that just kind of intuitive pigeonhole principle based stuff, no matter what we do, we're going to have greater than or equal to 2 nodes with in degree 0. Because we just don't have enough values to make it so everything's at least 1. We only have n minus 2 values to distribute among n nodes, and in that case, Like, we just can't fill all of them. So if we have this property, then what we can do is we can just kind of pick one of these nodes. Right, so when we remove this edge, we have some component here and some component here. And we have to add an edge from this component to this component, or this component to this component. So let's just pick any node with in degree I equals 0. Let's say it's, for example, this one, which it is. Then we can basically add an edge from any node in this component to that node. And it's going to make the in degree of this node 1, which is fine because they're allowed to be at most 1. But if we add this to some vertex which possibly has in degree greater than or equal to 1, then it's going to make it harder for us in the future, because eventually we're going to have to remove that edge. So instead we add this edge to a place where we're never going to have to touch it again. And that means that because we can do this, the number of edges we have to, the number of operations we have to do is exactly equal to only the number of edges we have to remove. Because we can do the operations that way. So now we'll say, how many operations do we actually have to do? Well, if IDI is less than or equal to 1, then we don't care about it, because we've already satisfied the condition for this vertex. So 0. Otherwise, if IDI is greater than or equal to 2, the other case, then we have to decrease it until it becomes 1. Or 0, but it would be easier to make it 1 because we can have something else be 0 and use strictly fewer operations. So we have to decrease until it becomes 1, which means the cost is IDI minus 1. We can summarize both of these in just the simple formula of the maximum of 0 and IDI minus 1. And thus the final answer is just the sum of all this, because all nodes are kind of independent of each other, since we don't really care about the edge we add back in. We only care about the edges we remove, and we need exactly this many edges to remove for each vertex. So we sum all that up, and that's the final number of operations we need to make the tree rooted. I guess you can say the sum over all I equals 1 up to n. Doesn't really matter, it's just the sum over all I. But yeah, that works. Okay. Now the next problem is very, very constructive. It's the robot problem, robot detection, I believe. And the way it works is you're given a, well, you know there's an infinite grid. And this point is, for example, 0, 0. You know there's some obstacle, and you specifically know that it's within this rectangle. This rectangle of size R by C. Notably, if you think of it like an array, this is the number of rows, R is the number of rows, and C is the number of columns. So we know there's exactly one obstacle here. For example, let's just draw it arbitrarily. What we can do is, we're going to give our robot a sequence of commands. And each command is either up, down, left, or right. We don't know where the obstacle is, but no matter where the obstacle is, we want to do the exact same sequence of commands. So that, for example, if the commands are like this, up, up, left, left, then the robot will go like up one, or sorry, to the right, and then to the right. Kind of mix that up. Yeah, but if the robot makes a move in which it's going to move into the obstacle, then it just won't make that move. For example, the obstacle could be here, then this could be up, and then this move to the right would move it into the obstacle, so we wouldn't move to the right. We would just stop here. And both of these moves to the right would be blocked. But it wouldn't like kill the robot. If, for example, we wanted to then move to the left later, we would just kind of skip these moves to the right because they're blocked off by the obstacle, and then later we would move to the left. And so what we want to do is, we give the robot this sequence of commands. Then, then we'll assume the robot performs these commands. And just from the final position of the robot, let's say, for example, some value of x and some value of y, just from the final position of the robot, we have to determine where's the obstacle. It's kind of like an interactive problem in a sense, but without the interaction part, we just have to show that it's possible to do that with some sequence. Important here are constraints. Rows and columns are less than or equal to 20, and the length of the sequence can be at most 10 to the 4. This is probably just because of the checker, because the checker has to have some way to make sure that this is actually valid. So the way to do that is to just kind of brute force all the moves out. And also brute force the position of the obstacle. But anyway, constraints are small, which means we can do some stuff with this. So how are we going to figure out the final position of the obstacle? Well, every final resulting x and y from the position of the obstacle has to be unique. And another thing to note is that this is a constructive problem. We can basically just do whatever we want with it. So if let like x naught and y naught be the final position if there's no obstacle. For example, the robot just won't run to any obstacles, it'll just be peaceful and do whatever it wants. Let that be the final position. But if there's an obstacle here, then the robot is going to have some of its moves be blocked. I forgot the original sequence already. It was like something like this. I don't remember. Some of its moves are going to be blocked. Which means that while it would originally move something like this, it wouldn't be able to anymore. It would be blocked off by the obstacle. So its final position can be said to kind of be offset by some delta x and some delta y. Some like changed x and some changed y. So we both want we want now for every position of the obstacle, every delta x and or delta y to be unique. We want this kind of ordered pair to be unique. So this is constructive, which means we can, again, do whatever we want with this. So why don't we just say, for simplicity, assume all delta y will be 0. Now, this is just a possible solution. This may not lead anywhere, but we're trying this because it could take us somewhere. So then all delta x must be unique. So this leads us into a construction like so, where we kind of give each row a range of values where the obstacle could be. Let's say we do something like this. So we move up, and then we move to the right some number of times. Then, if we do that, if we move to the right some number of times, then where we stop will depend on the position of the obstacle. Either it's not in this row, in which case we don't care, or it is in this row. In that case, if we move k times to the right, and the obstacle is in position I, then delta x is going to be equal to k minus I plus 1. You can do out that like the math by yourself to show how this works. Essentially, like if I equals 1, all the moves are going to be blocked, and if I equals n, then m minus 1 moves are going to be blocked. But yeah, essentially, we can make I minus 1 moves. That's another way to think about it. Out of k moves. And then the remaining k minus I minus 1 moves are going to be blocked by the obstacle, which is equal to k minus I plus 1. Yeah. So then, therefore, delta x is going to be equal to k minus I minus 1. So if we pick a different k for each row, then all we need to do is make k like different enough so that all of these delta x's will be unique. Because clearly, for between each row, all of the possible delta x's are going to be different among the row, because each I is different. So we can say that we can kind of find out the range that that using a k in a specific row will kind of sweep out. If we use a k, then delta x is on the range of, so the best case, or the lowest number of moves is when I equals n, in which case we get k minus n plus 1. And the highest number of moves is when I equals 1. Then we get k, and we just get k. Because k minus I plus 1 cancels out to just be k. So, essentially k is going to be on this range. Or wait, sorry, this should be m, not n. Because m is the number of columns we have. My bad. So k minus m plus 1. So this range is of size m. Which means if we start off the next interval at somewhere like, for example, k plus 1, comma k plus m, meaning we just add m to everything, then these two ranges are gonna have no overlap. Then if we start the next sequence sort of k plus m plus 1, k plus 2m, and we continue and so on, none of these ranges are going to have overlap. So all delta x's between rows will be unique, and all delta x's within rows will be unique, so all delta x's will be unique. And that's kind of it. All we have to do is start k at some big enough number that k minus m plus 1 is positive. For example, we can just say that in the row 1, k equals m. That works because k equals m. Then this is the value 1, this is the value m, so that's the range. The range is from 1 to m, and all those are valid values of delta x. Then on the second row, we can say k equals 2m. On the third row, we can say k equals 3m. On the fourth row, k equals 4m, etc. And basically all of this is going to work because there's no intersection between these rows. So the final algorithm is, for each row, move up, then move to the left some k times, or sorry, move to the right some k times, and then move back to the left some k times. We move back to the left so that we can start from 0 again, and if we hit the obstacle, then we may not necessarily start from 0. But that's fine because we've already hit the obstacle, so we know that our movements are going to be undisturbed like everywhere else. So it doesn't matter that if we don't actually return to 0, because in that case, we will have already hit the obstacle. So the move is n times go up, go to the right by k, go to the left by k, then keep going up, go to the left by some different k, like for example, this can be k1, this can be k2, and then to the right, k2 times, up until we reach the end. And with this construction, all delta x values are going to be unique, so every possible ending position will be unique. How many operations, or like what's the length of the sequence? You can show that it's on the order of like 8,000 something, so that's comfortably less than 10,000, so that should be fine no matter what. I think you can also get away with just like not moving to the right, but then you have to like kind of alternate. You have to go left, then right, then left, then right, and that part's kind of annoying, so I would say it's not worth it. Since it doesn't matter that you save half of the operations, because like it doesn't matter how many operations you use, you only need below a certain amount. So anyway, that part's fine, I suppose. But yeah, that's the final construction. We just go up, right, left, and then just keep going up, right, and left. Okay, the next problem I enjoyed a lot. This is probably my favorite problem in the set. You're given a permutation. For example, 1, 3, 2, 4, 5. What you want to do is split this permutation into 2 subsets. Where essentially we're going to split this permutation into 2 subsets, maintaining their original order, or like subsequences. So for example, we'll have 1, 2, and then 3, 4, 5. Actually, that's not the best example. We'll have 1, 4, and 3, 2, 5. In both these sequences, we're going to count the number of inversions among both of these sequences. And an inversion is basically a pair where a pair of indices ij, where I is less than j, but ai is greater than aj. So for example, in this array, these are the only 2 elements that form an inversion. This position is less than this, but this is greater than this. And it's kind of like, an inversion is kind of being out of place in the sorted version of the array. That's one way to think about it, but basically you just have a greater element before a lesser element. And if you count the inversions in both of these sequences, you want their totals to be equal. That's how it works. So what we're going to do is essentially figure this out. How are we going to do this? Well, okay, let's see what... The first thing to do is seeing if the permutations or the number of inversions are equal is kind of awkward. What we instead want to do is make it mathematically like more representable. So let's assume we have just everything in the first subset for now. Then the number of inversions here is just the number of inversions in the original array, which is 1. And then we'll say that the second subset is empty and it has 0 inversions. Instead of making these equal, what we'll do is we'll try to make their difference 0. And that's equivalent, but it's easier to work with because now we can handle changes more smoothly. So we'll say the quantity delta is equal to the number of inversions in the first sequence minus the number of inversions in the second sequence. Initially, delta is equal to the number of inversions in A, the initial permutation. And we want to make delta equal to 0. This is again easier to work with. So let's consider both cases. Let's consider a pair that doesn't form an inversion. What happens when we move 1 or both of these elements over? Well, if we move 2 over, then nothing changes. We don't get another inversion here, and because we're considering only this pair, we don't lose an inversion here. Same goes for if we move 4 over. So now we consider moving both over. We still don't lose any inversion among this pair, and we still don't gain any inversion because these elements are in order. So pairs that don't form inversions are kind of useless. What about pairs that do form inversion? Well, this is kind of a different case. Let's say, for example, we have this value here. Or we're going to consider this pair because this is the only pair that forms inversion. If we move the 3 over, we actually lose this pair because now the 3 is gone and we only have the 2 and it's lonely. So in an inversion pair, if we move the 3 over, delta decreases by 1. And if we move the 2 over, the same goes here because we still lose this pair. This pair is gone. So in either case, if we move one of the elements over, delta decreases by 1. And if we move both of the elements over, then we both lose this pair in this array and we gain it in the other array, which means that this inversion decreases by 1 and this increases by 1. So if we move both, delta decreases by 2. 1 element. And this is for 2 elements. So the change in delta is exactly proportional to the number of elements we remove in each pair. We can think of this in a different way too. And this actually may be more easy to think about. Let's figure out what happens when we remove 3. So we remove 3. Either 2 is still in the first array. In this case, we lose this inversion pair, so delta decreases by 1. Okay, otherwise, 2 is no longer in this array, so it's somewhere in this array. And we know that when we move this 3 over, it's going to be before because we maintain the original order. So this 2 has already been removed. Then when we remove this 3, this pair is already gone, so we don't care about it. But when we move this 3 over, now we gain this pair in the second array, which means that even though this doesn't decrease by 1, this increases by 1. So this is the convenience of using delta, because in either case, delta still decreases by 1. And this basically means that whatever we do to 3, it's independent of all other elements. It's independent of all the other elements that it's in an inversion pair with. Okay, we're very close to being done here. So now let Ci, the count of I, be the number of pairs that I is in, basically. So if we're looking at position I, either I is the first element, or if we have a pair AB, then either I equals A or I equals B. And also AB form an inversion. So we're interested in the number of pairs that I is involved, like the number of inversion pairs that I is in, basically. You can think of this kind of like if we make a graph out of all these nodes and we add an edge between every 2 vertices that have an inversion together, then it's going to be the degree in this graph. It's kind of a cool, different representation. So independent of all other vertices, when we move I over to the other side, delta decreases by Ci. Okay, that's useful. Why is it useful? Because we want to make delta 0. And all we can do is subtract some subset of Ci to make it so delta becomes 0. This is equivalent to saying we're going to take some subset of Ci that sums to like Ci1 plus Ci2 plus Ci3. This is our subset equals delta. So instead of subtracting all these values from delta, we're going to pick some, we're going to ask if it's possible to pick some subset of these values such that their sum is delta. And this is equivalent to subset sum or knapsack, whichever you want. And basically this problem is very well known, asking if there's some subset of values that sums to some given value. And we can solve it with knapsack, and that's it. We're done. Knapsack is well known, so I'm not really going to describe it here. So those, I think, are all the div 2 problems. Now we're going to move on to the div 1 ones. And these are harder, for sure. Basically, these 2 are like killer problems. Very hard to come up with like both the solution and to just prove it at the same time. Very hard to do either of them. First problem I'm going to do is FEWDIFF, few differences. Right there. So in this problem, you're given an array. For example, 1, 2, 3, 5, 5, 7. Doesn't have to be sorted. It just doesn't really matter. And basically, we'll define a subarray to be good if the number of distinct elements I don't know how I made that I sideways, which is kind of weird. But the number of distinct elements is less than or equal to, we'll say, some function of r minus l plus r minus l plus 1, which is defined as, so this is some function of the length, and it's defined as 1 plus r minus l plus 1 divided by 2. So if the number of distinct elements is less than f of length, which is this, then this subarray is good. Otherwise, it's bad. So basically, in one operation, we can change any element we want. And we want to find essentially the minimum number of operations to make all of the subarrays good. So the minimum number of changes. And, okay, well, so it's clear that this has to be possible, because we can make everything the same element using some number of changes, and then eventually it'll just be some, like, everything's the same, so the number of distinct elements is 1. Okay, let's kind of analyze the definition of good. Which subarrays can be good? Let's say, for example, length 1, small lengths. Because well, there can only be one distinct element. However, f of 1 is equal to 1 plus 1/2 is equal to 1.5. So in all cases, 1 is less than or equal to 1.5. So all length 1 subarrays are always good. The same goes for length 2, in fact. We can have at most 2 distinct elements, but f of 2 is equal to 2, and in all cases, 2 is less than or equal to 2. So all subarrays of length 2 are good. Can we say the same for length 3? It turns out we can't. Length 3, we can have 3 distinct elements, but f of 3 is equal to 2.5, which means if all 3 elements are distinct, then we have a problem. Yeah, we have a problem, because 3 is not always less than or equal to 2.5. So length 3 subarrays are the first interesting one. And if we look into it a bit more, the condition that no 3 elements are distinct is in fact very strong. Or no 3 consecutive elements are distinct is very strong. 1 second. Okay, let's say we have the condition that, for example, I'll put a question mark here because we don't know if they're all good or not. Let's say we have the condition that, let's say we kind of like build a subarray with the condition that all elements are distinct. Or, I mean, sorry, no consecutive 3 elements are distinct. That made no sense. So we'll start with some value, say 1. And here we have 1 distinct value. And then either we can put 1 down again, or we can put some different value down. Let's just consider both. So if we put 1 down, then we only have 1 distinct element. But here we can do whatever we want because both of these are the same. So if we keep putting 1 down, we're going to have a distinct element. So to get more distinct elements, we have to put something else down. So let's say we put, for example, 2 down. But now these 2 elements are different. So if we put some value that's different from both of these, we would have 3 distinct elements in a row, and that's not allowed. So if the previous 2 elements are the same, then the next element has to be equal to 1 of them. So if we make it equal to 1, then we have the exact same case where we have 2 and 1, and so it has to be either 2 or 1. So if we make it to 2 or 1, then we're kind of just like stuck in this kind of alternating sequence. What we can instead do is to try and get more distinct elements. We're trying to like maximize the number of distinct elements, and then we'll show that it's like not that many. So 1, 1, 2. So here, the best thing to do is to make this 2. So now we have more freedom, and we can make this whatever we want. Let's make it 3, and then we have to make this 3, and then we can make this 4, and we have to make that one 4, and we can make this 5, and etc. We can also consider the first thing we did initially, where instead of making this 1, we make this 2, and then we get the same sequence of things, except we use 1 fewer element. So this is kind of useless. This one's better. So the way it works is, basically, we start off with 1 distinct element. And then for every 2 new elements, we add in exactly 1 distinct element. So if this length is 8, then we get 4 new elements. If, for example, we have another 6 here, and we have 9 elements, then we can have 5 distinct elements. So we can summarize this kind of casework out as the ceiling of, if this sequence is length k, we're interested in the length of this one, which is length k minus 1. And so it's the ceiling of k minus 1 over 2. Mathematically, this is equivalent to the floor of k over 2. You can work that out on your own. But basically, the number of distinct elements we have is bounded above by 1 plus floor of k over 2. But you can now notice that this is always less than or equal to f of k, which is equal to 1 plus k over 2. And we can show that, like, if we have this inequality, 1 plus floor k over 2 is less than 1 plus k over 2, then we just make it so floor k over 2 is less than or equal to k over 2. And this is like the definition of floor. Any floor value must be less than or equal to its original value. So what we've just proven is very big. We just said, if all subarrays of length 3 are good, then all other subarrays are also good, because every other subarray can be thought of as being constructed using these kind of restrictions and a process like this. So because all subarrays of length 3 have to be good, and there can't be any 3 adjacent distinct elements, this bound works for all subarrays of any length k. So that's cool. And now it remains to kind of just well, now we have to use this information. Okay, so basically, now we're only solving for the problem of subarray length 3 is good. So all length 3 are good implies that all are good. Okay, let's continue. Now we can break this apart a bit more. Basically, we can show, and it's kind of obvious, that any subarray or any array, like our final array, is going to look something like this. It's going to be some series of consecutive elements, and then perhaps some alternating sequence of 2 elements in between. And note that we can't introduce a new element here, because then we have 3 distinct. So one of these final elements of the alternating sequence has to be either x or y. For example, it would be x, and then we continue a chain of x's, and then we can, if we have 2 x's in a row, then we can make, like, for example, some other element like z. Or we can make this a chain of y's. But essentially, it's going to be some groups of some groups of elements separated by these kinds of alternating sequences. Okay, now we're going to do a trick here. We're going to say of all optimal orderings, we're going to maximize the number of adjacent pairs in the final array. Why is that relevant at all? Because now this X is part of an alternating sequence. So actually, I'm going to move this over, and then we'll say that there's also an extra X over here, which kind of makes everything a bit clearer, I think. So then this whole thing is alternating. So this X is part of an alternating sequence. Right? But like, this is annoying because this has 0 adjacent pairs. If we can instead make this something else, then we could increase the number of adjacent pairs and not change the answer at the same time. So the only time changing this from X to something else, for example, Y, would change the answer is when the original value is equal to X. So if the original value is anything that's not X, then we can instead make this Y, which means we can now make the assumption that in the final array, any value in an alternating sequence has to be part of the original array. So everything's unchanged. Now this is nice to work with. Now we can deduce even more from this representation. Basically, we can show that, let's consider some alternating, let's consider some array x, y, x, y, and then we have some streak of x's. And then we have some, for example, zx, zx. What we're going to show is that for any element, say these are the elements in the original array, this middle element, there's an optimal solution where the middle element is either unchanged or equal to one of the original values of its neighbors in the original array. So essentially, AI is one of AI minus 1, AI, or AI plus 1. Okay. What's cool about that? Well, actually, first, how can we prove this? So we already know that every element in an alternating sequence is equal to its value in the original array, because otherwise we could change it and increase the number of adjacent pairs. So now we only have to show that this streak of x's and all other streak of x's, like analogously, they're also one of these 3 elements. Okay, now let's say the length of this is 2. We still want an assignment that maximizes the number of adjacent pairs. So if the length of this XX streak is 2, and there's no value in the original array equal to x, for example, we have a and b, then we can change these xx's to yz's, and we're going to have strictly more adjacent pairs, and at the same time not have used any more changes. So that's good, because that means that we've shown it for any streak of length 2. So the only time where this would be allowed to be xx is if it actually saves us a change operation, meaning at least one of these is equal to x. So Otherwise, the length of XX is greater than 2. And it becomes slightly more complicated, but not that much more. So let's say first we have XXX. Now consider the first two values. If both of these are not X, then well, what we can essentially do is, actually there's a bit more like annoying cases we have to do. So for example, XXX equals 3 is kind of a special case in my proof too. Basically, if there's no X among the first two, then maybe the third one isn't X. But what we can instead do is we can change this to the middle element. So we can change it to BBB. And that's fine because it uses the same amount of changes since B is also present even if X is. But in this like configuration, everything is equal to the adjacent B, which means that we've now just proven it for XXX equals 3. Because so what it means is among the first two and the last two, like one of these two has to be equal to X and one of these two has to be equal to X, otherwise we can find some better order. So either in the center is equal to X, in which case that's fine. We can just stay with XXX because all these are like adjacent to this X, or these two are X's, or some combination like this. And in any case, all elements are going to be consecutive to X's. Okay, now we can show it for XXX greater than 3. So for example, XXXX greater than 3. So we'll draw it out like this. We'll just assume it's 4 for now because it doesn't really matter. We can just stick some more elements in the middle. What we'll do is we'll focus on the first two and the last two. Now, if this is something like AB, where both of these elements are not equal to X, then instead of XX, we can make this something like AA or BB. And then this configuration will be optimal, more optimal, like better than better than XX, because here we use strictly fewer changes, and that's the most important part. So one of these two, at least one of these two must be X, and the same argument applies for the end. So now, the endpoints are kind of special cases, so now they're taken care of. And all we have left to show is that among any 3 consecutive elements, at least one of them is X. And basically, say none of these are X. Then they can be represented as something like ABC. But then we can change this to either XBB or BBX. And therefore we'll have strictly fewer changes. And so we know that we'll have either X's on the sides or they'll be different. And possibly it may even be optimal to change this to like BBB or something, or AAA or CCC. Well, actually no, probably no, it has to be BBB. So if none of these 3 elements are X, then well, we have a better configuration we can have. So basically, among every 3 consecutive elements, at least one of them is equal to X. Which means that which is equivalent to saying that every element is adjacent to one X in this group of X's. Which is equivalent to saying that every element is in one of these three values. So that's just kind of the proof. It's kind of like a casework bash, but it works out in the end. So yeah, because if every three consecutive elements have to be x, then we can say, for example, this left point is x. Then we can make these two not x, but then this element has to be, but then these three have to have an x in them. So now we have to put an x here, and so on. And so basically the x's will only be allowed to be spaced 2 apart, and that means that every element is going to be either equal to an x, or it'll have an x on its left or on its right. And think about it like breaking these into groups of 3, and then all of these groups of 3 are adjacent to the x in the middle. So it works out. Anyway, so that is cool. So now we can basically say that now we're going to use this observation to finally make our final solution. Note that both of the subtasks, note that there were 3 main observations in this problem. First, the length 3. Second, the observation about the structure. And third, the observation about there being only like this observation. And each of these observations progressively will give you a subtask. With only this, you can get subtask 1. With this, you can get subtask 2 of the very complicated DP that I won't describe here, but I describe in the editorial. And with this, you can get subtask 3 and therefore full credit. So how do we use this to get subtask 3? Let's say we built a prefix for the first I elements. So for example, and now we're looking to place the prefix of like a new element. Right? Well, if we're concerned about what this element has to be, we really don't care about everything before this, because this subarray of length 3 only contains these 3 values. So if we were to do some sort of dynamic programming, our state would only have to include the previous 2 values. But that's very, very nice, because there are only 3 possibilities for each of the previous 2 values. And similarly, there are also 3 possibilities that this value can change to. So we have O of n possible prefixes, and then it's times something like 27, some constant based on the number 3. But we have, say, O of n times 9 states, and then we have either 2 or 3 transitions. So if we were to do this DP, it would be O of n with quite a nice constant, or not the most amazing constant, but it wouldn't be a bad constant. And basically the transitions are either the previous 2 elements are equal, in which case you can change AI to anything, or they're not equal, in which case AI has to be equal to one of these previous 2. But we can also still use the fact that this has to be like one of these. So yeah, in this sort of transition, we can still use that fact, and we're basically only going to have 2 possible transitions. And maybe we ignore a transition if it means we end up using an element that's not one of the neighboring ones. Okay. This is all cool. And actually that's just it. This DP will solve the problem for full credit. So after all these observations, it comes down to a simple dynamic program solution. That's just kind of beautiful, honestly. There's so much work to break apart the problem and figure out what's going on. And there's still some substance to like the programming, but it's simple, it's refreshing. Actually, it's kind of like this for all the problems, maybe except for the last one, which I'm about to go into. And I will admit I don't have this proof like to heart. I don't know it by heart. So I may refer to my own editorial at some points and then just kind of like transcribe it to a video form. Hopefully you'll be okay with that. So what I'll do is I'll have this open and we'll open this up, not this, where is this? Add-on segment, and then okay. So add-on segment is the following problem. You're given a circular array of like A of some elements. And you're also given an array B of some other elements, some of which can be 0, and some elements in A can also be 0. But they're not negative. This turns out to not really matter, but whatever. So in a single operation, we can pick an index I. Sorry, I've got kind of a cough right now, if you couldn't tell from the rest of the video. We pick an index I, and then we pick some subarray of length I. Of length, Jesus, it's a terrible E, of length I. If it's like going to overflow because of the circle, it just kind of wraps around. So we pick a circular subarray of length I, and then we either add or subtract bi from all elements on this subarray. This is one operation we can do. We want to find out if it's possible to use some of these operations to make it so, if it's possible to use some of these operations to make it so all elements are 0. We don't care about the minimum number of operations, nor how we do the operations, only that all elements are 0. Okay, so what's with this? This is kind of whack. That is, like, not every change affects some subset of the array. And okay, so we're going to use kind of a cool mathematical argument here. And actually, I'm going to kind of do the proof backwards from how it's described in the editorial. Well, it's kind of a flow that makes more sense, I think. Okay, so first, actually no, I'll stick to the editorial, I guess. That makes the most sense. So first, let Ci be the difference between AI plus 1 and AI. If it's a circle, it's just kind of like, again, wraps around. So AM plus 1, A of M plus 1 is equal to A1 in terms of just terminology. So once we do this, then we have 3 conditions. 1, for all prime powers p to the k that divide some value of bi, we're going to use this notation, this bar notation for divides. For all p to the k that divides some bi, actually I'm going to use numbering here. We must have the following property. Let D be the GCD of n and the GCD of like I of all of the I where bi is not divisible by p to the k. That is, p to the k does not divide bi. And this bar notation, like a crossed out bar, means that it's not divisible. Okay. Then for every I less than or equal to d, the sum of ci plus ci plus d plus ci plus 2d up to n is divisible by pk. So for all I less than or equal to d, this sum is divisible by p to the k. So p to the k divides this. And that's the first condition. This seems very, very arbitrary, but it will show up later as we kind of show that we can, with these conditions, construct the final array of zeros. Second condition is, it's very similar to the previous condition, except now let d equals the GCD of n and the GCD of all I. How does this work? It's like I subject to I don't remember how this works, but it's basically like it's all I where, I'll just say such that, yeah, it's the GCD of all I such that p to the k, or bi is not divisible by p to the k. Okay. Now here, we let this be the GCD of I and what is this? I such that it's something like bi is not divisible by, or bi is greater than 0. Okay. It should be 0. Then for all starting positions I less than or equal to d, the sums of the form ci plus d up to n are equal to 0. Again, this will come in and be relevant later. We're going to take a kind of similar approach to how we proved the directing a tree problem, rooting the tree, because we're going to show that these conditions are both necessary for the answer to be possible and sufficient. That is, if these conditions are satisfied, we automatically have an answer. So 3 is basically let d be the GCD of all I times bi over n. Okay, now for all prime divisor p of d, yeah, not specifically prime powers, then say n is divisible by p to the t for some maximal t, and d is divisible by p to the k, then these sums, a1 plus a p to the t plus 1, it's kind of weird to draw, plus a 2p to the t plus 1, etc. And of course, this doesn't have to be 1. It's any number any number I less than or equal to D, all of these sums must be divisible by p to the k. So p to the k divides all of these. Now these are the conditions. If we can check this, we're done. So the actual solution is just checking all these conditions, but proving it is much harder, or it's more complicated, I guess. So I'm going to kind of briefly sketch this out instead of going too full in detail, because otherwise we would like just this would be incredibly long. So the way we show that they're necessary is the final state of the array is all zeros, which means that all ci are also equal to 0. So we can show that any operation isn't going to change any of these conditions. If these conditions were true before, then they'll be true after any operation. Which means that if an array is valid, then these conditions will be true for an array 0, which we'll show right now. And actually, it's kind of obvious that they're true, because like 0 is divisible by anything. And at the same time, the sum of a bunch of zeros is 0. So it's automatically satisfied for all ai equals 0, which implies all ci equals 0. But then also, we have that these conditions don't change even though we do operations. So if it was true before, it'll still be true, and if it was false before, it'll still be false. Basically, we utilize the fact that ci is a difference array. So either the value, so if we add on some range, then only two differences are going to be changed. This is going to be a plus, for example, bi, and this is going to be minus bi, or the signs could be flipped. Because we can make bi both positive and negative, or we can both add and subtract it. So for the first condition, we just need to maintain this divisible by p to the k. So basically the idea here is either bi is divisible by p to the k already, or essentially, because of the way we define d, these two differences are actually going to be on the same one of these sums, which means that we both add and subtract the same value, so we end up with 0 change in total. So it won't affect the total sum. That's the first one. The argument is basically the same for the second one, because any I where bi is not 0 will be on the same sum. Well, like the two elements will be on the same sum, so the total sum will still be 0. And the third one is, I think, slightly more complicated. Yeah, basically it's just some argument with like prime divisors. Basically, all I would do in this video is just like kind of write out these formulas, but they're already written down, so there's not much point in me doing it if it's not visual. So yeah, this one you can read on your own or just deduce it. So now we've shown that we can show that these conditions don't change even when we do operations. So these conditions are in fact necessary for an answer. Because if they aren't true, then like we couldn't go from 0 and do some operations to get to that array, because the conditions are guaranteed to be true for any array with like zeros. So all valid arrays have these conditions true, meaning if any of these conditions are false, automatically we know it's invalid. Okay, but how do we know this is enough? For example, how do we know that there aren't more conditions that we're missing out on? And the proof of sufficiency is even like wackier. Okay, I'm gonna get rid of this part. I'm gonna outline it because I think, yeah, I'm gonna outline it in kind of a proof stuff format instead of like going over the whole thing because it's kind of a lot. I don't want this video to be way too long. So first, we consider only C. What we want to do is we want to make all C equal to 0 somehow. Also, we're assuming that these three conditions are true, because if not, then we automatically don't have an answer. So we want to make all CI equal to 0. Right now, CI is arbitrary. It's just based on the input. First, we can, because this is a difference array, it's basically, doing an operation basically entails picking two elements, x, y, such that x minus y is equal to I, or x minus y is equal to the GCD of some I and n, because we can construe the operations that way. Then we just we say Cx plus equals bi and Cy minus equals bi. Then now what we basically want to do is we want to make all Ci divisible by the LCM of all bi. So LCM of bi divides all Ci, which is equivalent to saying the LCM of all bi divides the GCD of all Ci. Okay, so now basically we'll show this possible by saying if some number Ci is divisible by a, where a is equal to p to the k, or a is divisible by p to the k minus 1, then we'll show that we can also make Ci divisible by a times p. We can make it so a times p divides Ci, and thus we can get an additional one of those prime factors. And basically the way we do that is another like clever trick. We find some value bi, given some value bi, we find some value bi such that bi, like bi divides bi, big bi. It's also divisible by a, and bi mod p to the k is equal to p to the k minus 1. We can use like Chinese remainder theorem or just something to show that this element, that this value of bi always exists. And then once we have this value, we can essentially, whatever we can do, we can pick any x and any y, and then we can add like p to the k minus 1 to bx and subtract it from by. And we can make it so we can affect any elements where they're like the GCD of it's like the GCD of all of the indices where it's like not divisible by this p to the k. We can affect any elements like in this array, but we can't affect elements between them using only elements from this array. So basically here we invoke condition 1. And ultimately it's only possible to do this if all of these values modulo p to the k are equal to 0, which means that they're divisible by p to the k, which is condition 1. And if these sums are all 0 modulo p to the k, then this is a cool analogy by Anton. It's kind of like you're given an array where the whole sum is 0. And in one operation, you can do subtract 1 and add 1 to sum two elements. And then you want to make the whole array equal to 0. It's the exact same thing, and it's just as solvable. So okay, now we can assume that the LCM of all BI divides all CI. So now I definitely recommend like reading this more because this video explanation is not the most thorough. So we basically just use the exact same argument but with the second condition to show that we can now make all CI 0. Because the second condition basically implies that it's kind of like the same type of sum just with a different like argument, but we can still use it to make all CI equal to 0 because all of those individual sums ultimately end up being 0. Note that this is only possible if the second condition is true, which we assume it is, because otherwise the sums wouldn't be equal to 0 and we would either have a harder time or just not be possible to make it at all. But if the second condition is true, we can always do this. So now we have that all CI is equal to 0. Again, by the same argument as the previous making CI divisible by the LCM of BI, except now we use the second condition. Okay. So now all CI equal to 0, which means all AI are equal. So this is actually where subtask 1 comes in. So basically we consider this quantity D equals GCD of all I times BI over N. Because if we're going to use a specific I and we're going to like apply it to the whole array, then the best, like the lowest K where we're forced to add like Ki to the whole sum, like ideally we would want Ki to be equal to N, but sometimes we can't do that because some subarrays are not divisible by N. So the lowest K is equal to something like N over the GCD of N over I. Then the total effect we have on each element is Ki over N. So if we substitute this in for K, we get Ni over N times GCD Ni is equal to I over GCD N and I. And multiplying this by BI because we have to have that effect. Oh wait. Yeah, this shouldn't be N, my bad. This should be GCD of N and I. Kind of miswrote that. Okay. So consider this quantity. Basically, let like x be a1 equals a2, etc., because all the elements are equal. Then, if x is divisible by d, we're done. And because of condition 3, we do know that x is divisible by d. That's a typo. So, yeah, basically, This is something cool. And the reason x is divisible by d is because we can again consider like all the prime factors. Basically, consider some prime p, then let x be divisible by p to the t, I think that's what it was. Yeah. Or actually, we'll say n is divisible by p to the t, and d is divisible by p to the k. Then the sum we're interested in for condition 3 is a1 plus a p to the t plus 1 p to the t plus 1, etc. is equal to n over p to the t. That's the number of elements we have. And then because all the elements are x, it's just that. So we know that this quantity from condition 3 is divisible by p to the k. But n is divisible by p to the t. So, and in fact, p to the t is the largest p that, or is the largest value of t that n is divisible by. So in terms of just p to the k, we can kind of like get rid of this. And therefore, p to the k divides x. So every prime factor of d also divides x, which means that d itself divides x. And we've shown that it's possible. Okay, that was very long-winded. Yeah, I didn't exactly go over the first part of the proof that much. So you can, again, check out the editorial itself, just for that. But that's basically it. For the whole solution, we checked those 3 conditions, and we've just shown that they're necessary and sufficient, so that's it. Okay. Yeah, that concludes the editorials. Hope you guys enjoyed at least the earlier ones. Maybe this one was a bit incoherent, but the other ones should have at least been better. Okay, goodbye.